So today we'll be starting this probability reasoning. Okay. So to go in the details of probability reasoning, first let's revise some basics of probability theory. Okay, because that is necessary for this. Okay, so some basics. So first comes is sample space. So if you recall from your probability course which you have taken uh, earlier, so sample space it's a collection of all possible events. So let's say capital X is equal to x1, x2 till xn. It's a collection of all possible events. Yeah. And the sample space can be discrete or continuous. So now what is the probability? So when we say P of xi, so what this means or what this refers to? So it is basically the likelihood of an event xi to occur. Okay, and it's a non-negative value. It could be zero, but it could not be in minus, so less than zero. It's a non-negative value in range of 0 to 1. And total probability of sample space is 1. Okay, so taking a simple example, so if we consider the event of dice throwing, so what could be the possible outcomes? So 1, 2, 3, 4, 5, 6. This could be the possible outcomes. So all the possible outcomes set. This is known as sample space. And for a particular, for example, this is xi. So what is the probability that the outcome would be 3? So xi equal to 3 is because here all are equally probable. So it's 1 by 6. Okay. Next is for mutually exclusive events. So if you remember, so for mutually exclusive events, the probability for at least one of them is sum of their individual probabilities. Probability of at least one of them is the sum of their individual probability. Okay, and we have this known as experimental probability. Experimental probability. So which is based on the frequency of events. So for example, if we are performing some experiments, we don't know what would be the outcome, or whether let's say we are throwing a dice and we don't know whether the dice is thrown or not. In that case, we are conducting an experiment, and We calculate the probability of a particular event based on the frequency of that particular outcome out of all the events. Okay, so it is based on frequency of events. Second is subjective probability. Subjective probability, it is based on expert assessment. Okay. Second, and next comes is compound probabilities. So compound probability, it describes independent events. Independent events means that means there are no causal relationship between them, so they are independent of each other. Okay, so which do not affect each other in any way, and joint probability of two independent events. Joint probability of two independent events. Okay, so this A and B. Okay, let's see this. P of A and B would be number of times A and B occur together out of all the events, out of all the this is the size of the sample space basically, and this would be since these events A and B are independent, so this would be equal to PA into okay, and this NS refers to all the number of elements in the sample space. Okay, so for example, consider this case. Um, let's say we have this kind of remote, you can say, and here there are three keys, and we can press any one. And this is, let's say, a display which display either A, B, or C. Okay, and these are the probabilities. P of 1 is, let's say, 0.6, P of 2 is 0.2, and P of 3 is 0.2. So you can see the sum of these should be 1, as these are all the events of this sample. Okay. Similarly here, P of A, let's say it's zero point 0.6, PB, let's say it's 0.3, and PC is 0.1. Sum is 1, right? And we're considering that these events are independent of each other. Okay, whatever key we are pressing and whatever is getting displayed, there is no link between them. They are independent. So if we are calculating what is the probability that we have pressed one and A is displayed, so since they are independent, it would be P of 1 into P of A, and that would be 0.6 into 0.6 into 0.36. Okay. Now, second comes the union probability under this compound probabilities. So sorry, union probability. Union probability says P of A union B equal to PA plus PB minus PA and B, or A intersection B. And since we are considering A and B are independent events, so PA plus PB minus this would be PA into. Okay. So in the same example, if we want to calculate P of one union or one or A, that means P1 plus PA minus P1 and A, or V P1 comma A, which we have just calculated. So P1 is zero point 0.6, PA is zero point 0.6 minus P1 comma A is 0.36. Okay, so this would be that. Now there are some axioms in probability, some basic axioms. Let's recall them. So probability basic axioms. So number one, it's a value between 0 and 1. PE, when we're saying PE, so PE denotes probability of event E. Probability of event E. Now, when we consider this P of true event, so it is always 1, and P of false event, it's always 0. So this is a certain event, we can say, and this is impossible event, not just uncertain, because uncertain event has some probability, but this is impossible. That's why its probability is 0. Next is that P of an event A would be 1 minus P of negation, right? So all this you must have studied before. So P of A, so yeah, P of A union B equal to PA plus PB minus PA intersection. Okay. Now next comes is conditional probability. Condition probability. So conditional probabilities, it describes dependent event. As till now we have considered that we have the independent events, and based on that we have drawn these formulas or these arguments. But now we are considering uh, dependency. It describes dependent events, right? So dependent events means they have a causal relationship or may affect each other in any way. Okay. So conditional probability of event, it's basically denoted by PA given B. That means what is the probability of event A given the event B has occurred. So this is P of A intersection B or A and B by PB. That is the formula. Okay, so this PA given B is referring to the probability of event A given that event B has already occurred. Okay, so now there are something known as prior versus conditional. Prior versus conditional probabilities. So So prior probabilities of events A and B is PA, comma PB. Okay, but if we know that A for sure, then probability of B might change because they are dependent on each other. So if we know that A has occurred, A is true, then this probability of B might have increased or at least get affected. Okay, so this is what we represented by P uh, P B given. That means what is the probability of event B has occurred given or if we know that A has occurred. Okay, so for example, uh, let's consider this D event that doorbell rings at midnight. Okay, and this event W says that Mohan wakes up at midnight. Now, if we know that prior probability of event D is 0.001, prior probability of event W is 0.01, and the probability that Mohan gets wake up at midnight given the doorbell rings at midnight is zero point 0.8. That means 80%, in 80% cases, if the doorbell rings at midnight, then Mohan gets wake up. Okay. Then, if we want to calculate P of D given W, that means what is the probability that if we know that Mohan gets wake up at midnight, then what is the probability that that is because of doorbell rings? That means we are trying to say that we know the conclusion that Mohan wakes up at midnight, but we want to uh, identify or we want to calculate the probability that Mohan gets wake up because of the doorbell rings. So for this, we have something known as Bayes rule. Bayes rule. Okay. So what Bayes rule says? Bayes rule says that P of A given B is equal to P of B given A into PA by P. So using this Bayes rule, how we can calculate this? We can calculate this by P of W given D into PD by P, and that would be equal to zero point 0.8 into 0.001 into divide by 0.01, and this would result in 0.08. Okay, that means there are just 8% chances that if Mohan gets wake up at midnight, that is because of the doorbell. Okay, and from here, if using this Bayes rule, if you see that P, A, and B is equal to P A given B into PB. So if you recall this one, so from this formula, PA and PA intersection B would be equal to PA given B into PB. Okay, and similarly, PA given B would also be equal to PB given A into PA. Yes. So now let me take another example to clarify this base rule if you have any doubt. Uh, for example, consider this that consider these two events that A event says that the patient has COVID infection, okay, and B event says that patient, when we are saying patient, so we are referring to a specific X. Patient has loss of smell and taste. Okay, now now uh, we should have this a priori probabilities with us, which is like what is the probability, prior probability of uh, COVID infection? What is the probability of this loss of smell and taste with us? Okay, and we should have this that what is the probability that like out of all the COVID infected patients, how many patients have that loss of smell and taste? Okay, so basically P of A and B. Okay, so uh, then if we just calculate that P of B given A, that would be equal to, for example, let's say this is point 0.6, and this is point 0.9. That means 90% of COVID patients have loss of smell and taste. So that is just for an example. So what is P given A? That means what is the probability that patient has loss of smell and taste given the patient has COVID infection? It says that P of A and B by P, and that is 0.9. Okay. Now these events A and B are independent if P of A given B equal to PA and P B given A equal to P. That means the probability of event A given that B has occurred would be equal to the probability of event A because A and B are independent. So A do not have any dependency on B. So B has occurred or not occurred, A doesn't affect. So that's why this information is useless for in that case. So the probability of A given B would be equal to PA. In that case, if A and B are independent, similarly for PB given A, if PB given A and A and B are independent, so whether A has occurred or not, it doesn't affect the probability of event B. So that would be equal to probability of event B. And using this information, we can say that therefore P A and B would be equal to PA into PB in case A and B are independent. Okay, and coming to the joint probability, we can consider this. So this is A, negation A, B, negation B. So this is point 2, point 3, point 1, point 4. So this is basically what is the probability of A given B, probability of A given negation of B, probability of negation A given B, and probability of negation A given negation B. And you can see the summation of this is 1. Okay, this is the joint. Now, what are the advantages and problems of probabilities? So, advantages. So, advantages are it's a formal foundation. It's a reflection of reality. Reflection of reality when we talk about a posteriori. Okay, and what are the problems of probability? So problems are they may be inappropriate. That means future is not always similar to the past. So they may be inappropriate because we are calculating probability of a posteriori probability. That means predicting the possible outcome based on the past sample results. So but future is not always similar to the past, so that's why it may be inappropriate. It may be inexact or incorrect sometimes. So that means especially for subjective probabilities. Okay, and that's it. So when we are referring a posterior probability, so let's see. So we have some event, and based on that is not event. Let's say we have some evidence, and that evidence is concluding some hypothesis. So now we have PE, we have PH, the a priori probabilities, and we also have what is the probability of E given H. Then, so all this is a priori information or a priori probabilities, and based on this, when we are trying to find out what is the pH given E, so that is a posterior. A posterior. Okay. Okay. So now we have to start. That means we have to go in a little more detail uh, um, using the Bayes theorem. So we have already seen the Bayes rule, right? So now let's see the extended Bayes theorem. So extended Bayes theorem. So what it says, let's see that. So P Hi given A. What is this? So this is probability that hypothesis Hi is true given evidence E. Okay. So what is the P E given Hi? So this is probability that we will always observe evidence E given hypothesis hi is true. Okay, what is the probability of hypothesis hi? So it is the a priori probability that that hypothesis hi is true in the absence of any specific event. In absence of any specific evidence. That means it's a priori probability. It doesn't we didn't find any evidence. What is the probability that hypothesis hi will be? And okay, and we are considering k is the a number of all possible hypotheses. K is number of possible hypotheses. Okay, so what extended base theorem says the probability of hi given E would be equal to P of E given hi into P of hi divided by summation over all the hypotheses. Let's say we are considering j j equal to 1 to k is the number of all possible hypotheses, and e given hj into p hj. So this is the extended base theorem where we consider all the hypotheses to calculate the probability for a particular hypothesis. That's why we're considering all the possible hypotheses. Okay. So for example, if we are considering that this S has patient has spots, this S is referring to this, M is referring to that patient has measles, and F is referring to that patient has high fever. Okay, and this measles as actually affecting it, that measles is creating spots and measles is creating fever. That means when someone is infected with measles, so it gets these spots and fever. So these are the evidences for measles and also for fever. Why? Because if someone has spots, then obviously there is a chance that it can affect from measles, and it can have an additional symptom of fever. So this is a additional uh, evidence. So this, so if a person has spots, so it increase the belief in favor of fever. And if both spots and fever are present, so they provide evidence in favor of measles, but they are not independent. They had a little dependency on each other. So we can't say that these two events S and F are completely independent. Hence, we cannot simply sum their effects, but can take conditional probabilities of their conjunction into account. Okay. So basically, this measles is creating spots. Measles is creating fever. Okay, and these two events, this E1, E2, this E1, E2 together are concluding some hypothesis which is measles, and but they are also having additional dependency relationship. So in general, given a prior uh, given a prior body of evidence E, so in general, given a prior body of evidence E and some new observation capital E, we can uh, okay. Before that, let's see that belief network. Belief network. So what is a belief network? So belief network, it's a representation of causal connections between different events with associated condition probability. Okay, in this belief network, nodes represent events, nodes represent events, and uh, the directed edge, the directed edge from node A from node A to node B, it represents the fact that event P may be an effect of event A. Okay, and conditional probabilities for a node is provided for each possible value of its parents. Okay, so that is a belief network. That is a belief network, and uh, that is a belief network. And uh, uh, let's see some properties of it. So uh, I'll explain you the belief network in detail with an example. So don't worry. So let's see some theory first of it. So properties of belief network. Okay. So it's a DAG. That means it's a directed. It's a directed acyclic graph. Okay. Uh, in this nodes with or which have no parents. So nodes which have no parents have prior probabilities, have prior probabilities, and all other nodes have condition probability. Okay. In general, there can be multiple directed paths between a given pair of nodes in belief network. So I'll do one thing. So uh, let's stop here today, okay? And I will share this the explaining of this belief network, which is also known as Bayesian belief network, because it follows the Bayesian approach. So I'll share this Bayesian belief network in a short video, and that would become clear to you within a right? And yes, some this Bayesian approach that this network that we're going to study this follows. So we have a couple of points related to that also. So let's see this Bayesian approach. This is the final thing that we will do today. So this Bayesian approach so derives the probability of a cause given a symptom, and let's derive the probability of a cause given a symptom. It has gained importance recently due to advances in efficiency because it actually requires a little more computations. So as the computational power has increased now, we have better systems. So it has gained importance recently uh, because now it's feasible to implement Bayesian models, right? Um, Especially they are very useful in diagnosis systems. Useful in diagnostic diagnostic systems. So, for example, medicine, computer help systems. Okay, and they use inverse or posteriori probability. So, inverse to conditional probability of an earlier event, even that a later one has occurred. Okay, they use inverse or posteriori probability. Okay, okay, then let's stop here and uh, I'll share the Bayesian belief network solving with an example in a short way.